thank you for the introduction, and thank you for the opportunity to present the Beneq and give some idea about the ALD, atomic layer deposition. So my talk today is about thin film technology called atomic layer deposition, especially spatial atomic layer deposition, which we can use for really fast and high volume manufacturing for optical films. So the work is one of my colleagues in Finland, Dr. John Röhn. He's one of our optical material experts and also ALD expert, and works as a process development engineer at Beneq. Beneq truly is home of ALD and all about ALD. So we are almost all dedicated to atomic layer deposition. We have more than 30 years of industrial expertise in-house. We have a big facility shown here in the picture in Helsinki area in Finland, where we have more than 40 ALD systems for ALD production and R&D purposes for our customers. Our headcount is roughly 200 at the moment. And in the US, we operate in Boulder, Colorado, where our office in the US is. And I'm the president there. And my personal background is in ALD, so I have a PhD in ALD from ALD materials and also the technology development. So for us, knowing that optics is everywhere in our daily life, from consumer products to energy applications, and all these manufacturing and production methods for optical components are well established by means of low cost, low temperature, high throughput, and excellent uniformity by current the thin film deposition methods are there. But what we are really missing is a conformality on 3D structured substrate and surfaces. And if we look at this, by means of applications or examples, we talk about the different types of micro nanostructures, gratings, sidewalls, free-form optics, high curvature lenses, optical domes, tubes, and rods. So all these type of shapes are somewhat difficult to deposit with existing or more conventional thin film deposition methods. And looking at this from technology point of view, so the PVD truly line of sight deposition method is not capable of depositing 3D objects. In CVD, we are able to do that somewhat. But in ALD, we can control the surface of 3D objects with extreme uniformity and conformality, regardless what shape or size the object is. So the ALD, it's been studied and investigated and used in many type of applications, from microelectronics to various type of nanotechnology applications and optoelectronics. Also in photonics, there's one example of my colleagues John Röhn's work on waveguides, where the ALD can really accurately be used for the control the physical distance in slot. Like in this example of showing the example of waveguide here, and in the right side picture is about combining that the controlling the physical gap, but also the adding the amplifying layer, which here is the erbium doped aluminum oxide. Beneq has also studied a lot of ALD and used that for developing the conformality of objects on macro scale, An example here given is on dome type of structure. So this is a batch ALD reactor, in this example having 3 dome objects, and we have shown the batch non-uniformity less than 2% for mostly used optical oxides, this is very recent work that we have been doing in the field of optics. So just a few words about atomic layer deposition. So it basically is a chemical vapor deposition method where we control the film growth on the surface. So it's based on saturated surface reactions, and the precursors on the surface are released alternatively. And this example here is for the titanium dioxide using the 2 precursors, titanium tetrachloride and water. So in first step, we basically saturate the surface with the titanium tetrachloride precursor, and in the second half of ALD cycle, we introduce the water as an oxidizer that saturates the first monolayer of titanium dioxide. And this also defines how the accuracy of ALD is, so we can really grow the film by 1 molecular or atomic layer accuracy in thickness. And same comes to conformality. So more today is about the spatial ALD, which can be really used for ultra-fast production. So ALD, conventional ALD, is something where the deposition rate is low, but by means of getting that better, we can use the ALD in a spatial mode. So in spatial ALD, instead of having all the substrates or our objects in one batch chamber, we use the chamber where these precursor zones are separated, like shown here from our tool, and then the schematic on the right side. So in this case, we basically rotate this plate where our substrates are passing through the precursor zones, and depending on what rotation speed we have, we can determine the deposition rate. And taking the spatial mode compare that to the conventional or traditional ALD in batch, we can basically cut the ALD cycle time from several tenths of seconds from several tenths of seconds to fraction of seconds. So it really is the faster way to do ALD. So our concept for spatial ALD is called Benec C2R. So it is a rotary spatial plasma enhanced ALD system. So deposition rate there is several micrometers per hour. The system can handle 7 pieces of 200 millimeter size wafers or a larger number of smaller objects. We can use this tool for lenses and other 3D type of objects with thickness of 30 millimeter. It has exactly the same thickness, uniformity, and conformality control than batch ALD or conventional or traditional ALD. And the tool can be equipped with the automated substrate loading or attached to the cluster for the industrial production. So the latter part of the talk is about the work that we have done to demonstrating the optical or oxides for optical films. So this is about the silicon dioxide, tantalum and titanium dioxide, which have been deposited at low temperatures up to 150 this graph is showing the deposition rate. So ALD is always it's a chemistry driven and a chemical vapor deposition method. So our chemistry define what the actual growth rate is, and that's why we have a different growth rate for these films here. So the optical, these oxides, they really result in a good quality when it comes to optical properties. And their optical loss is low. And films typically in ALD, since we control that in monolayer by monolayer, we can create extremely smooth films, and also with the high accuracy. So one example here is for anti-reflection coating. Based on this design here, the stack thickness is roughly 1 micrometer, deposited at 85 centigrade on polycarbonate and BK7 class substrates. So rotation speed in the system has been 200 RPM, and the total deposition time for this example stack here is roughly 18 minutes. And the results here are shown as the reflectivity on this spectral range, and showing that the reflectivity is less than 0.1% in between the 460 and 615. We've also studied the high aspect ratio structures with this technology, and this example is using the test structure roughly 20 aspect ratio. So the trench is 120 micrometer deep and 5 to 7 micrometer wide. So all these three oxides have been studied, and we have measured the thickness on top and also on the bottom of the trench. And this graph is summarizing the results for silicon dioxide, tantalum pentoxide, and titanium dioxide. So depending on the chemistry and material, there is a little bit difference of this thickness ratio between bottom and top. But as we can see, the silicon dioxide, for example, regardless of rotation speed or the deposition rate, it results exactly the same thickness on bottom and top. For tantalum oxide and titanium dioxide, the chemistry it's not that favorable than for the silicon dioxide, and we can see then with the higher deposition rate or rotation speed, we sacrifice the film thickness on the bottom a little bit. So I would like to summarize the work. So the ALD technology really offers the excellent film deposition characteristics for optics, and especially extremely good conformality on both micro or even nano and macro scale. The spatial ALD technology overcomes the low deposition rate compared to the traditional ALD, and is really the route for faster production of optical components with extremely good conformality. So if you have any questions, we are here from tomorrow at booth 307. And please feel free to send any question to author of this paper, John Ron, or me, Tommi Kääriäinen. And as said, we are happy to see you at our booth tomorrow, 307. Thank you very much.